Welcome to my channel, students. Today we are going to discuss about circuit families topic in unit 2 of VLSI design. So the circuit families under this topic we are going to discuss about static Cmos circuit. Actually the static Cmos circuit what we are going to discuss is the AND and OR functions can be converted in terms of NAND and NOR. And how we can convert this is by means of the technique called bubble pushing. And also we are going to discuss the concept called compound gates. So where this compound gating concept is useful for performing the complex functions, that is you can perform complex functions at the same time you can able to calculate their logical efforts. So first we will discuss about bubble pushing concept. So bubble pushing concept, for understanding this we are going to use De Morgan's law. And before that we must know one thing. Generally the CMOS circuits they produce an output that is of inverter type. So CMOS circuits are inherently inverting. So and OR functions must be built from NAND and NOR gates. So using De Morgan's law, we know that A dot B the whole bar is equal to A bar plus B bar, and also A plus B the whole bar is equal to A bar dot B bar. So how can I draw the gates now? So actually A dot B bar is nothing but it is an output of NAND gate. You can notice. So the output of NAND gate is nothing but it is A dot B the whole bar. Correct? At the same time the output of NOR is A plus B the whole bar. Output of NOR. Okay. So how I can represent by using De Morgan's law? So NAND gate it can be represented as A dot B the whole bar is equal to A bar plus B bar. That means the OR of two inverted inputs. That is the meaning, no? A bar and B bar are the two inverted inputs that must be ORed. So I can draw the diagram like this. So the OR of OR gate I am drawing. Two inverted inputs I am giving. So I draw the bubble at the input side lines. So A bar, B bar. So this is my A bar plus B bar gate. That means the equivalent of NAND is nothing but inverted input of OR gate. That's all. Similarly, for an NOR gate. So the second gate is NOR no. A plus B the whole bar. It gives the output. So the NOR operation can be represented as by using the De Morgan's next law, that is A plus B the whole bar is equal to A bar dot B bar. So you find that A bar dot B bar, that means the function is AND. So draw an AND gate and then invert the inputs of those two AND gates. So and it gets inverted inputs A bar and B bar. So that we put the bubble at the input side, A bar and B bar bubble. And finally you get the output as A bar dot B bar. So using the De Morgan's law we get the gates like this, the equivalent gates. For NAND gate, NAND is equivalent to an inverted input OR gate. Similarly NOR is equivalent to inverted input AND gate. So with this we are going to do the bubble pushing concept, so that we can convert all our basic gates into NAND and NOR function. And we know already NAND and NOR are called universal gates. With these gates you can able to implement any kind of functions, any logical operation on any logical function you can perform. So we need to convert all the small basic logical gates into NAND and NOR form. And finally we come to a conclusion. So NAND is equivalent to OR of inverted inputs. NOR is equivalent to AND of inverted inputs. So now we will see an example. So design a circuit to compute F is equal to AB plus CD using NANDs and NORs. So you have to design a circuit which computes the function AB plus CD, but the circuit must contain only NAND and NOR. Okay, so that is you can convert either full of NAND or full of NOR. So we'll discuss how to derive that from the normal function. Generally we know AB plus CD in the sense AB, it is AND of two inputs. CD, it is another AND of two inputs, C and D. And these two must be added, plus symbol is there, no? So they must be added with an OR gate. So this is the general gate expression for the given function f. And now our work is using bubble pushing concept, we have to convert this into NAND form. Okay, so for that you first have to understand one thing, so that is this topic, that is whenever you get an AND function, if you find AND function in the logical circuit, we have to use the bubble at the input side. So put a bubble at the input of input, at the output side. So for an AND gate you have to put the bubble at the output side. And if you find OR gate in the circuit, you have to put the bubble at the input side of OR gate. So remember these two things. So in the first step, what you are drawing is, you are just drawing a circuit for the basic logical gates, using basic logical gates. And then in step 2, I am going to use the bubbles, as I said already, AND and ORs. Based on AND and OR, I am going to place the bubbles. So since I have two AND gates, so I place the bubbles at the end of the two AND gates. And I have one OR gate. So for an OR gate, at the input side I have to place the bubble. So I place the bubble at the input side here. You can notice. So at the input side I place the bubble, and in here and at the output of NAND I place the bubble. Then later in step 3, what I have to do is, whenever, at the output of an AND gate you are putting the bubble. Now wherever there is a bubble, you have to put an inverter. That is the rule. So in bubble pushing you have to use the inverter wherever you have put the bubble. So at the output of AND gate there is a bubble. So here I have to put an inverter. Okay. And at the input of OR gate there is a bubble. So for that I have to put an inverter at the input side of this OR gate. Similarly in the lower path, the output of AND gate will get an NOT gate. And then for the input bubble of OR gate, I have to put another NOT gate. I think you noticed this. So then continuation. So finally what you get is, whenever we have two inverters sequentially connected, you think what will happen? For example, if I give one as my input, what I will get as the output? The inverter output would be 0. And then this 0 would be fed into the next inverter. So the next inverter would produce the same one. So whatever the value you fed, that you will get at the output side when you connect two inverters in series. So whenever two inverters in series comes in that line, you can omit that inverters and you can straightly connect the line, because there is no change in output. So I omitted those inverters path. The two inverters, no, we can simply remove the inverter and connect a line. So we have removed the inverters and connected the lines. And one more conversion here is this last gate. What is this gate? So this is an ORed, input inverted OR gate. Correct? So the input is inverted OR gate. So the input inverted OR gate is equivalent to which gate? So I have already told you, no, the inverted input OR gate is equivalent to a NAND gate. So instead of using this OR gate, inverted input OR gate, I can replace it with another NAND gate. So now my circuit has completely turned into NAND form, NAND function. Okay, so this is what we require now. Because using bubble pushing concept, what we have to do is, we have to convert the AND and OR function into NAND and OR function. So finally we have got all the functions in terms of NAND. So this is all about the bubble pushing concept. And in continuation to that, we'll discuss about the compound gates. So compound gates is nothing but in Cmos technology, I said. So it is helpful to find out the logical efforts of various inputs, and the logical efforts can be estimated for AOI 21, AOI 22 and some complex circuits also. AOI means AND or invert logic, and A for AND, O for OR, I for invert. A 2-1 means how many inputs the gates are having. So based on that the number will come 2-1, AOI 2-1, AOI 2-2. And for complex AOI gates you can simply write as AOI. So here is an example given for an unit inverter. So we know how to draw an inverter. It is an PMOS connected with NMOS, and then the logical inputs, logical effort at the input is, since inverter has only one input, the logical effort of the inverter is, see in input capacitance, the input capacitance is 3, and also the input capacitance of inverter, the normalized value 3. So the logical effort GA at the input side is equal to 3 by 3. And parasitic delay, so I have already told you to calculate the parasitic delay. So parasitic delay is nothing but the diffusion capacitance, C out. Parasitic delay is nothing but C out divided by the input capacitance of the inverter. The capacitance or C out divided by the inverter's capacitance. So C out is 3 here, see here 2 plus 1 3, and then the inverter's capacitance value is 3. So C out by say the inverter's capacitance 3, so which is 3 by 3 parasitic delay for the inverter. And then similarly the next circuit is AOI 2-1 circuit. That means the function, it implements the function y is equal to a dot b plus c the whole bar. Example for AOI 2-1 logic. That means you have AND function, then OR function, then invert function. AND OR, then invert with 2 input and 1 input. Okay. So A, B are 2 inputs. First AND, you have to AND the function, and then you have to OR it with C. So an OR gate is used. Finally you are going to take a complement. So I use a NOR at the output side. Okay, the NOR is nothing, OR, the output must be ORed, at the same time it must be inverted. So I use a NOR gate. So this represents my compound function for the given expression, the compound gate function for the given expression. And then now we will discuss about the Cmos expression for this circuit. So we know A dot B. So when you find a function with A dot B, that means you have AND gate. So whenever you are implementing the Cmos gate, so you must clearly understand, first you have to finish the pull down network, that is the NMOS part. NMOS part you have to complete, and later that you just have to invert the part and draw it invert it and draw for PMOS component. So here the A dot B component, when you find the AND function, so the A and B must be connected in series. So I connected two NMOS with A and B inputs in series. So here you can find A and B, two inputs connected in series. I'll tell about the sizes later. So first I connect two NMOS in series, and then A dot B is ORed with C. So whenever you get OR function, you must use a gate parallelly. So A dot B is ORed with C. So the C function must be connected parallelly. So it is connected parallel to this C. Okay, so C NMOS is connected parallel to AB. So now the pull down network is over. So you have to continue with the pull up network. So in the pull up network, what we have to do is just invert the connections. So if you have connected A and B in series in pull down network, just connect the two PMOS in pull up network parallelly. You could notice here A and B were series in the pull down network here. So the same thing now I am drawing as parallel in the pull up network. And then earlier C was connected parallelly with AB. Now C must be connected series with A and B. So I have to connect a C gate with the PMOS, C input with the PMOS gate series to that. And we have to finally take the output at the junction Y. So that's how this is how we have to finish the Cmos implementation for the given function. Once you finish up the Cmos implementation, what we have to do is we have to assign the sizes of these gates. But most of the problems, they will give the sizes to you. If suppose the sizes were not mentioned, you have to identify the sizes. So already I said that for an NMOS transistor, the size must be, you have to assign the size as, that means you have to find the size as, the resistance of that NMOS is R by K times. K is the size of the MOS. So for which value of size, if you put the size value K here, some value, the entire NMOS must have the value of total resistance R. So entirely how many transistors you are connecting, but the total network must produce the resistance of R value. Totally it must produce R. Similarly, the pull-up network, it has to produce the total resistance R value. So in such a way you have to choose the gate sizes. So if I choose K, the gate size as 2, what I will get? R by 2 I will get, no. K, if gate size is 2, R by 2 I will get. So at the input side R by 2 and B input side another R by 2. That is at A you will get one R by 2, at B you will get one R by 2. So totally when they are connected series, you will get total resistance R value. Okay. At the same time you may ask, what about C? So the C resistance, C is connected parallelly to this A and B. Under worst case, whenever we have parallel connections, at any time one ring must be, one line must be in on mode, no. That is, one line will be connected. So either this first line AB line or this C line must be connected. So that is the parallel logic, no. So considering that case, if the AB line is not connected, then C line alone must be connected with the output. So if C line must be connected now, what size I have to choose? So C is only one resistor, only one transistor, so with one resistance. So R by K size I have to choose 1. So if I choose 1 only, then only I will get the total resistance R. So since the two branches are parallel, at worst case delay, one branch is connected to this, that means only the C is connected now, it will give the entire resistance R value. So I can take that, I can maintain the resistance as R. Similarly for the pull-up network, so when it is coming for pull-up network, the size of the transistor I mentioned as 4. Why? Because for pull-up network PMOS, it is, the resistance is 2R by K times. So K, if I assume K is equal to 4, what will happen when I put K equal to 4? I will get R by 2 resistance here. So 2 resistance parallel. When I put K equal to 4 here, what I will be getting? R by 2, R by 2. And since the two resistors are parallel, any one is going to be connected. So assume that only one R by 2 is going to be connected. So if only one R by 2 is going to be connected, then the rest of the resistance C has to provide how much resistance? It must provide R by 2 resistance, so that the entire total resistance will become R. So to make C as R by 2 value, again I have to choose the MOS value, K size as 4. So 2R by K, when I put K value as 4, I will be getting one more resistance R by 2 here, over here. So out of the two parallel branches, one R by 2, and then in C branch, in C input, one R by 2. Totally it will give R resistance. So the resistance is maintained, R resistance value is maintained here. And by the way, we have to calculate the logical efforts. So the sizings concept I explained now for these CMOS circuits. Once you have finished the drawing, then later that we have to calculate the logical efforts. So we know very well the logical effort is nothing but, it is C in, input capacitance. So now we have to calculate the logical effort at each and every input. How many inputs here you have? 3 inputs, A, B and C. These 3 are your inputs, no. So at each and every input we have to calculate the logical effort. So when it is A input, see what is the input capacitance? 4 plus 2. So 6 is the input capacitance. C in, divide it with the input capacitance of inverter. The input capacitance of inverter is 3. So 6 by 3. At B input, see the B transistors. So the B transistor, this is with size 4, and here the B transistor with size 2. So the input capacitance would be 6 divided by the inverter's capacitance 3. So we will be getting 6 by 3. Similarly for C, it is, for C you can notice here the size, the PMOS size is 4, NMOS size is 1. So 4 plus 1, 5 divided by the 3 inverter's input capacitance. And the parasitic delay, for calculating parasitic delay, what you have to do is simply you have to check the output capacitance and divide it by 3. Okay, so the output capacitance value, how you have to calculate? The output capacitance is simply calculated by taking, see what are all the resistors, the capacitance that are connected with Y. So 4C connected, and here from here 2C, and here 1C. So totally 4 plus 2 plus 1, 7. So 7 by 3 is the parasitic delay for this gate. Okay, so in this AOI logic, we have first implemented the compound gate function, and then the Cmos implementation of the given circuit, then the sizings were made, then later that we calculated the logical efforts and parasitic delay. Thank you, students.